So, very good morning, all. Let's resume back to where we have already done the programming. So, I'm sure now you are much more comfortable with greedy algos and you have got the basic clarity of the fractional knapsack problem. That is what we have already discussed in the last class. I hope you have implemented that and this has been clear. So continuing with the same, today we will discuss another very interesting problem and which will make the concepts more clear. That activity is called, the problem is called as activity selection problem. So let me explain the problem first. And once the problem is clear, then from there, I will explain how it is greedy and how to solve that. I say, effectively, I have set of activities available to me with certain properties, etc. And aim is to find out or select maximum count of activities or maximum activities to be scheduled. So what are the constraints? It will be clear. I want the maximum activities to be scheduled, but the constraint being, let's say, in the same place, let's say in the same lecture hall. So activities, let's assume there are different lectures of different duration, but all of them are to be scheduled in same lecture hall. So that is a constraint. And what are the activities? So each activity has, say, activity AI. So I'll say each activity has some start time and each activity has some finish time. To give you the data, let me just put it as I as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For convenience, I'm using the same data which is used in the book. So the values which I'm using are same, so that whenever you read from the book, you find it much more easy to revise and understand. So I'm just using the same data. 2 and 12, and then the finish time is also available with the data available as given this. So you can easily see this is the various timing given to us. So I want in the same lecture hall maximum activities to be scheduled. Can I schedule, say, 7 activities, all 12 at a time? Obviously not. Can I schedule 11? I have to check some 11 sets which can be scheduled. So scheduling effectively will mean that activities should be non-overlapping. And non-overlapping as per the timing. For example, activity A1 finishes at 4. So A4 can start. They are non-overlapping. I call such activities as compatible activities. But if I say A1 is going on, A2 can start, non-compatible because they have overlapping period. As I can easily see, A1 finishes at 4, but this starts at 3. So till A1 does not finish, A2 cannot be started, and A1 will finish at 4. Hence, A2 cannot be started, and that's why A1 and A2 are not compatible. Similarly, let's say A4 finishes at 7. So A4, A7 not compatible, but A4, A8 are compatible. A4, A8, A11 are compatible because each of them has non-overlapping period. A4 starts with 5 to 7. A8 executes 8 to A7. A7 means this. Sorry, A8 means 8 to 11. And then A11 means 12 to 14. So even if I have some activity starting at the same time, for example, I say A2 is 3 to 5, then immediately A4 can also start 5 to 7. So A2, A4 are also okay, compatible, because this finishes at 5. So 5th period held, and then from 5th to 7th period, the other teacher takes, so they are compatible classes. So I want maximum activities to be scheduled and maximum activities which are compatible with each other. Compatible with each other to be scheduled. Now, if this is the aim to be done, obviously I have to do some programming and do that. First of all, I can easily see it is a permutation and combination problem. It is an optimization problem. We have to maximize the set of activity size. So maximize we have to do. So I can easily see many characteristics of our previous discussions related to DP problem or greedy are applicable. But now I have to find, is it a DP problem, or it is a divide and conquer problem, or is it a greedy problem? Yes, you have to probably think of this. Now, if you can find best greedy choice, if you can guaranteedly find greedy choice, obviously this is best. But can you guaranteedly find? But question is, can you guaranteedly find? For example, for this problem, what is your intuition, logic? Some choice. Maybe you say job with least time requirement. Meaning finish time minus start time. That the job which takes minimum time, that should be scheduled. That can be one solution, one greedy choice. Yes, could be the best choice, but could be the best. Good word is not good. Intuition works in life, but never accepted in algorithms. Because on basis of intuitions, you take some decisions. In life also, mostly they work, but sometimes they may not work. Sometimes it might not be best. If not best, then the best solution is not being achieved. For example, if I say I have a problem which could have been solved with, say, maximization value could be, let's say, 25 achievable, and intuitively, if you go for certain logic, and if that was not a greedy choice, you might get 23 or 21 answer. Nearly best, but not the best. So if greedy choice was not best, then you might not get the best solution. Why? Because a greedy algo decides, it always makes a choice that looks best at present, that looks best in the current situation, looks best at the moment. Now, why? And I hoping that this remains best, or this will be useful, that this local optimal solution, I'll say hoping that this local, so this was a local choice at the moment, this local optimal choice actually leads to the global answer, or leads to the global optimal solution always. Yes. So this is hoping that if guaranteed, if this hope or this choice was guaranteedly best, if guaranteedly best choice, that means greedy algo is best. Greedy algo is best and applicable. So my local choice, if the local choice was not optimal, if local choice or greedy choice was not guaranteed correct, we will achieve near optimal solution, not always the best optimal solution, not always the best, but that will mean that in algos, the best algo was still possible. Hence, you have to decide in every algo that if you go for a greedy choice, if you are guaranteeing only, then you should go for that choice. If you are not guaranteeing, then maybe you have to think of a better solution. For example, this problem, I say, if I have the best choice, obviously greedy will be useful. If not guaranteed, then go systematically. So first of all, I will go maybe step by step. Maybe I'll find DP solution to be possible, or divide and conquer to come. And then if I'm able to make a good greedy choice, maybe I can do that. First of all, step. Obviously, I have to find optimal structure. And obviously, optimal structure to use optimal substructures. And if they are overlapping, the DP can be one way. Optimal structure to be decided. So I say, I want certain activity selection to be done out of some jobs given to me, let's say from I to J. So if I have, let's say, I as 1, J as n, I want certain activities or count of activities. What should be the optimal structure? Aim is to find out a structure so that you have the corresponding constraints satisfied, but recursively, I'm able to proceed towards the substructures. Obviously, our starting point is assume some AK is known to you. Is known, and AK is guaranteedly in the answer. So that is a special power given to us by the gods, and I'm using that power through which I decided that. So I assume that I know this answer. That means activity AK will be selected. So I just use capital A, so that initially I said capital A is the activity. So AK activity selected. Now, AK selected means corresponding to its start and finish time, other activities may be selected accordingly. So activities finishing before AK's start can be now considered as one sub-problem. Similarly, activities starting after finish of AK can be again another sub-problem too. For example, if I say AK is, let's say, some activity has starting time as 5 and ending time 8. So from AI onwards, this side, I will find activities whose finish time is less than equal to 5. They can be coming from one sub-problem. And this side, I should get an answer whose start time is greater than or equal to 8, that will be again useful for me, the sub problem 2. So my sub problem 2 and sub problem 1. Now I can see some substructure which can be again used here, some visible. So I have to formalize this, that if I say my AS to be found for some ij, I would like to apply the same AS over some ik minus 1 or k, then one AK is guaranteedly selected, and then same thing I would like to apply on the other side of ASK plus 1 onwards. Now, if I want to formalize this, so I will say, let's formalize this to make initial definition also, so that we can implement at least brute force solution and then try to see whether DP can work or not. So this substructure based, I will say, I wanted my AS1 to n also to be selected. In general, I can say AS1 to n will be a function or ASIJ. But how will I formalize this start and finish? Because 1 itself is undecided, n is itself undecided. So I will say, let's add a dummy two activities, activity A1 and AN plus 1. Dummy activities I will add, which will help in solving my problem, where I say, sorry, A0 and AN plus 1. A0 has start time, has a finish time as 0. AN plus 1 has start time as plus infinity. The advantage of making this is all activities are guaranteedly compatible with both of these. So I can guaranteedly claim that every activity is compatible, because A0 finishes at time 0. So any activity can start from 0 onwards. A infinity starts at plus infinity. So all activities can finish before plus infinity. So all activities are compatible. So effectively, my problem says find AS of 0 to n plus 1, or equivalently, I write AS 0, n plus 1. It means set of or maximum set of activities which can be scheduled or which are compatible. So they are compatible, effectively means can be scheduled within these constraints. The purpose of this is that through this, I will be able to say that AS of some I to k, where less than this 0 or plus this greater than 0 will be possible, less than j will be possible. So this will tell activities compatible with AI and AK. And compatible will automatically give the corresponding implementation logic to be implemented. So I can say this notation helps me to find compatible activities answer set, and same recursive definition will be possible. So effectively, my second step of making the recursive definition, or I'll say optimal substructure, now becomes possible using sub problems. I say, if I want to find out AS ij, effectively I is equal to 0, j is equal to n plus 1, then I want to find out certain activities which will be found compatible with I2 k, I claim, plus one activity which is AK plus AS K2J. So this becomes my answer. if I know K. I assumed that this is known to me. I have assumed AK is known to me, known through special powers. So I say this, that now my AS can be recursively found or optimally substructure found. This is a sub-problem 1. This is a sub-problem 1, a sub-problem 2. I wrote ASIK instead of not K plus 1 or K minus 1. Reason being, I said compatible with AK. So K is already selected. It will mean activities compatible with AI and AK. AI means A0, everybody compatible. AK means now activities compatible with AK. So if in order of finish time, I am assuming my jobs. If I assume my jobs in order of finish time, then I can guaranteedly say if A5 gets selected, let's say whose time was a 5 to 7, all these activities are guaranteedly having finish time less than equal to finish time of A5. They are already listed only like this. And this side, obviously, finish time is order of finish time and accordingly. So that is already guaranteed. Now I say compatible will mean only to check that ASIK means activities whose finish time is less than or equal to A5's start time. Because K is the last activity, like AN plus 1. AN plus 1 has a start time infinity. So my same definition of ASIJ, that also had same definition for AJ. So the same definition is still applicable for this K, and I need not write K plus 1, K minus 1. Similarly, I say ASKJ, not K plus 1J to be written now, means activities compatible with AK and AJ. This is meaning that activities are starting after AK. AS0 n plus 1 also meant activities starting after A0. Here also it means activities starting after AK. So AK is compatible, and I am able to say once AK will finish, other activities to start after AK. So knowing this, I can easily see that if I want ASIJ to be calculated, of course, initially I will be called as 0 and J will be n plus 1. I say this will be equal to nothing but corresponding answer coming from IK plus 1 because of activity AK already selected, and third answer will come from ASKJ. So if this sub problem gives value of the set to be C1, this gives to be C2. So my count of activities will be actually nothing but that will be simply equal to C1 plus 1 plus C. This is sub problem 1. This is a sub problem 2. And this is activity AK. So total activities selected will be these many. So my ASIJ will be again dependent on sub problem 1, sub problem 2. All obviously they will be overlapping sub problems. Hence it can become a DP problem also. Knowing this, now I can easily say that if I have to implement it recursively, I need to find K. How to find K? Because K is not known to me actually. If I don't know K, obviously try all Ks. And that is what we always do in MCM, in LCS also we did same, try all K. Like in MCM, I said from K, I plus 1, I to J minus 1, etc. So I'll say, now I can effectively go to step 3 and I can probably define the recursive definition of the solution in a way that if I want to find ASIJ in general, it means a total set of activities which are compatible with AI and AJ. This will be equivalent to some non-recursive value. Otherwise, for all K, so I say effectively AS, I'll put it on new page so that it becomes much more clear. So I'll say ASIJ to be equal to AS of IK plus 1 plus AS of KJ, activities compatible with AK and AI, activities compatible with AK and AJ, plus one activity, this total count will be this answer. If recursive, otherwise non-recursive we will find here. Non-recursive we will find how can we have the non-recursive one. But K is not known. So effectively I will say try for all K maximum and for all K. And what can be the K limit? Obviously, K will be in between I and J. I is a 0, J is n plus 1. So K will never be equal to 0 or n plus 1. And accordingly, K can be initially 1 to n. Once any job gets selected, leaving that job, others will be in between attempted for all permutations. If not, when non-recursive, at that time I say if there is only one activity, obviously nothing to be selected. So if I say it will be returning a 0 if no activities are to be selected at all, when will be that condition? Obviously based on I and J, because I have already sorted the data based on finish time. So I can say if I greater than equal to J, it means that I have reached to a situation where you have only one activity left and one activity left effective or 0 activity left, and one activity left also means that activity has been already guaranteedly selected. If only one left, K will become equal to these sides later and then nothing to be done. So if I have reached to a condition where I am only talking of either A0 or A1 or let's say A6, if a call comes to A6 to 6, that will mean A6 has been already selected and now beyond A6 I have to combine, because if A6 call comes, that job is selected and compatibility with A6 is being considered, means A6 is already over. So at that time, no further job will be compatible because nothing is left on the sub problem size. So I can say this. Now, brute force implementation directly possible on based on this. Brute force implementation you must try. It's a recursive top-down approach. And you can definitely do this. And try it. And you will be learning through this, similar to MCM or similar to LCS. So similar to MCM's top-down approach implementation, this is there. Now, once you have done this, later now we say, is it a greedy choice? Is there a greedy choice? So you can easily smell now that you had one greedy choice already decided, that based on the corresponding minimum execution time or minimum time needed. I say, yes, that probably could be, but can I guarantee that was the best choice? Yes, if you can guaranteedly prove that it is safe. So if you are able to prove that it is safe or it is best, then greedy algo is applicable. I ask you, let's say if there was a job which was executing from 0 to 6, but other jobs or other activities were starting after 6. Now, is this activity good enough to be selected or not, even if long? Answer is, this activity is still the best choice, because this activity disturbs no one else. If so, then why should not I select such a job? So that can be another greedy choice. So I say one criteria could be that let's select the job or select the activity with minimum finish time, with least finish time. If I select that job, I claim that this can be probably the best choice. Why? My logic is it will give other jobs maximum possibility or other activities maximum possibility to be scheduled, because it has least conflict or overlapping for the rest. It will finish first, so remaining time will be much more higher, and it will give others as a maximum possibility. So that can be another greedy choice. I have to find out which choice is the best and prove. For example, proof of this greedy choice to be the best is given as a theorem 16.1 in your book. You must read that proof and understand it from the book. But what it says is that first time, obviously, it is obvious that first time, whichever job has finished earliest, that will be the best, no doubt about that, because once it is selected, it, even if it is executed, others are not being disturbed through this, so they can be taken. But counter logic could be, if I don't select this, then I will say instead of this, some other job will be selected that will finish later than this, that reduces chances of others to be scheduled with the maximum probability. So hence I can probably think this is a good logic. So I will formalize this now greedy choice. I will say at any time, no, first time obviously, but at any time, a job with minimum finish time is best choice, provided job with minimum finish time is best to be selected if it is compatible with already selected choices or activities. Of course, that has to be there, only then it is worth. And those activities which have been already selected, I claim that they were already the best. Hence, there was no question of repeating or replacing them. So this can be another way. So I say every time it's a local choice and currently best. And because it is guaranteed correct, hence, so it is local choice. It is currently best and guaranteedly correct. Hence, greedy algo is best. If a greedy algo is best, we can expect this to be even faster than a DP solution. Otherwise, of course, a DP will be much faster normally, but in this case, it will be faster than DP solution. And otherwise, DP solution could have worked. So in this case, if you say this, effectively, one sub-problem will be empty. That is another property which we have already discussed. Like if I say I selected some activity AK, the left side sub-problem is empty. Because the corresponding activities in the left side, they have their finish time, which is less than or equal to the corresponding finish time of this job. So once I selected current job that will finish at this time, say it finishes at 9. So all these jobs are finishing less than equal to 9. If this job is being executed or selected, these jobs are not to be selected because they will also require their start time as well as finish time to be before than 9. So I will say initially I have already sorted these jobs. Let's say I selected some job which is finishing at this time. Out of this, whichever were compatible, they are already selected. The compatibles have been already selected, and now I have to look only in the remaining jobs. One sub-problem empty, so obviously overlapping problem over, no overlapping sub-solutions because only one sub-problem. Overlapping sub-problems will never come, and hence DP issues over. Because there is only a single sub-problem, because we have now one single sub-problem only. And obviously, based on that logic, things become easy and I can easily implement that way. So once having said that, my logic is simple. Now I say, okay, my greedy choice is known to me and I have proved this is best choice. So safe choice I have proved through the theorem 16.1. And now I say greedy implementation to be done. So obviously iterative as well as the corresponding recursive, both logics are possible. And once I know this, probably the previous A0, AN plus on all that, etc. now can be safely avoided. So let's go one by one. Let's go for an iterative implementation first. And then we will understand partly the recursive also. I will say, of course, I have activity selection to be done, array of activities to be passed to this as a parameter. Along with array of activities, I and J will also be passed. Of course, initially I will say this is going to be equal to 1 and this is going to be equal to n. Ideally saying no A0 or AN needed now, or AN plus 1 needed, because now my logic is not recursive. Hence, I have effectively no need of having these dummy problems. I can directly solve this easy. But IJ I'm just using so that it looks generic that you can call this. Activities, it will be a structure having the start time and finish time. So now I hope you can easily implement this logic without difficulty. What will be the step first? Yes, obviously sorting your activities, sort ARR on basis of finish time. Then obviously first job will be guaranteedly selected because that is going to be used always. So I can say, okay, my selected job is currently selected, index is the activity 1. And then now I have to check, can I select activity 2? Can I select or not? What will be the condition? So I'll have to check if the corresponding new job, that is, say, next job is some next variable. So next variable is, let's say, 2. So I'll say if array next dot start time, if this starts after the finish time of selected job, of course, this job can be selected. I'll just put this side. I'll just partly fold it. Yeah, so it is visible now. So I say if array next current job's start time is greater than or equal to the already finished job, obviously this job can be selected. So if it is selected, my selected variable will change. And next time I will compare only with the last selected, because last selected compatible means previous are already compatible. So selected will be changing. My counter can change accordingly. If not, if selected, obviously selected changed, next will be accordingly there. If not, it means this job is not to be selected, selected will continue. That means now I will need a loop outside for next to change. So next will be starting from 2 and going up to n. And accordingly, if next variable is selectable, the selected variable will change, and next comparison will be for the last selected activity. If the activity was not compatible, this will be rejected, and initial selected will continue, and effectively I can go like this, and finally I will be returning the count. More than this code, I think I need not write, and you can probably do that. Time complexity, you can easily see in this case, if you have to sort, sorting will take n log n for a general sorting algorithm, and greedy algo, after sorting, how much will be the greedy algo's time complexity. You can easily see effectively loop times of n. For each job, I have to take a decision whether to select or not, and accordingly, only one iteration is good enough. Having said that, going further, just think of having the corresponding recursive version also. So I'll just talk of having int activity selection, recursive version. Of course, here also your array will be needed. Your I and j will be passed. Of course, initially, I will be calling it with I as 0, j equal to n plus 1. So initial call is made with these variables. I assume, again, sorting will be done outside because I should not recursively sort it again, sorted on basis of a finish time. So that sort call also should be outside. Once done, effectively means my selected job is which one? My last selected job is I. And now I have to find and up to j. So I have to effectively find an activity from I plus 1 to k, I plus 1 up to j maximum, or up to j minus 1, yeah, before j I will say, because j is n plus 1 initially. So before j, which is compatible with selected job, with ith job or ith activity. So now what I mean, so I will say selected equal to I. Next, which I am trying to do is obviously I plus 1. Then obviously now I have to check correspondingly whether next jobs or next activities start time if it is less than ith job's finish time or selected finish time. I'll say selected or ith, whatever you write is one and the same thing. If it is less, what I have to do? It means this job cannot be selected. Cannot be selected means I have to effectively go to the next job. Next job means I have to loop, keep on repeating this process, but make sure that you don't go beyond J. So before J, you have to stop. So that condition also you have to put somewhere. And as soon as you got job selected, if you found a job or if you found an activity which was compatible, that means next was value correct, next found, then you will have count plus plus, and then you will have next count, or I will say count plus equal to recursive call to be given. So count also, either you can have a global variable, or I will say simply, I can say return 1 plus activity selection with recursive, same array being passed. The only change being I has changed. Now next job was the recent selected. Up to J I have to go, and from here the recursively the answer will be found. 1 plus because of the current job selected, next job has been selected or next activity has been selected. So that will add 1 count to this. And that will be the overall logic. Beyond that, I need not write the code. I will say, ask you to try and do, but let's look at its time complexity. So you could find it's a recursive call, recurrence tree or recursion tree can be used, but I say still aggregate analysis will be simple. If you see aggregate analysis for all jobs or all activities, it will be called once and exactly once. Once and exactly once. Every activity will be checked starting from 1 onwards. 0 and n plus 1 are implied. And 1 onwards, 1 will be selected or iteratively ignored. Then 2 will be selected or ignored. If selected, selected will mean recursive call. Ignored will mean +1. Then you go to 3. Again, either recursive or +1. You go so and so up to n. You will go either recursive or this. But if you have, let's say, 2 to 5 activities ignored, so loop executed, ignored, 6th onwards, the recursive call will come. And if that recursive call comes 6th onwards, still I can say aggregate wise, my total analysis means order of n only. To be precise, only n times the loop will execute in total, including recursion call also. So this whole totality will total execute by all recursions n times for each particular activity once called. On the other hand, if you had implemented a DP solution, obviously you needed AS a 2D array because I needed 2 dimensions to be passed. So 2D array will be needed. Each ASIJ will be generated. Most likely it is going to be correspondingly O of n square, because each of ASIJ will be calculated. So I can see O of n square logic there. With the greedy algo takes order of n, sorting time separate. So of course, if you include sorting time also, still it becomes order of n log n. Hence, I can say best or better than DP, but provided if greedy choice was best, if applicable. If greedy algo was not applicable, obviously it will not be the best solution, even if better time complexity. So better than DP in terms of a time complexity also, and optimal answer was guaranteed. Optimality you have to guarantee. Only then you will go for this particular algorithm. So having said that, I will wind up, and effectively I will ask you now to do some homework for all of these problems. So I'll say, what is the homework? First of all, the brute force implementation of the same logic you should try. Of activity selection, and we have already discussed that it will be recursive and inefficient, trying with many sub-problems which obviously overlapping and will be recalled. Then I saw that a greedy choice was possible, so you can implement iterative greedy, and greedy iterative choice, if you remember, leaves effectively one sub-problem only. One sub-problem is left. So effectively overlapping problem was over. I'll just talk of this when talking of it, recursive. So recursive implementation of a greedy also should be done. This automatically has shown one sub-problem remaining of the right side only. Only on the right side we were using, and that automatically ensures no overlapping calls will come, no unnecessary calculations will come, and the right side sub-problem will be solved only. Once you do this, I will suggest you to read the proof of theorem 16.1, and then there are two problems given in the book 16.1-1 and 16.1-2 on page 421 and 422 of Corman's book. So you should try those problems also for your practice. Having said that, you do all these. Next class, we will discuss another interesting problem on greedy, and after that, we will start with the next strategy of backtracking. Bye-bye. All the best to all of you. Let me stop now the recording and